So welcome everybody for this final presentation from EPFL and this consortium. It's the second phase of a 4-year project in total since 2022. So with that, I think you will show the rest. So
thank you very much. Welcome everybody to this final presentation of the REACT project. To give a first broad context to know why this project came to be, there are more and more objects being launched into space, and so more space systems to design, and most of their environmental impacts will be decided by design choices made early on in the design phase. And so this is also where we can have a positive effect by making design choices that are reducing those type of impacts. And this is why also we have started this activity a few years ago, and are using life cycle assessment and life cycle insights into the design of future space missions. So the purpose of this final presentation is to give a description, an overview of the entire project, what has been done, what were the activities, the main results that we achieved. And we will also, in the second part, do a demonstration of the software. And also Valer introduced the purpose on its side for showing it to a public audience also. And the agenda will be organized in this way. We have 2 parts. The first one lasting about 1 hour and 10 minutes, where we will introduce the project, also explain the results in terms of methodology and theory more, how the tool was built and what we can do with it. Then we'll have a break, and at that time we can also collect questions. There will be QR code you will see. And in the second part, it's more of a live demonstration showing the features of the tool, and then concluding and keeping some time for questions at the end also. And so let's start with this first part, introducing the project, the consortium, and what has been achieved. With first a little bit of background. So I'll let Marnix start.
Yes, so in terms of background, this project was decided by EPFL, which you might know. In case you don't know, it's the Future Launch Preparatory Program, essentially the Future Launchers Department. And they Valer saw a need, and the rest of the department, for LCA in the future, because I'll show it to you later, regulation-wise, it's coming up more and more. And with EPFL Space Center focus on space sustainability in general and in LCA as well, the EPFL Space Center was chosen for this task. And the end goal was really to make a tool which can be used by the industry also beyond. So the project we're showing you now was the development of the tool, taking into account industry feedback. But the goal is for it to be used also after the project directly by the industry. So a bit of background: when we started the project, the second phase of this project, this was how the legislation landscape looked like and how promising it looked like in the European sector, and it is a growing trend towards sustainability. So the EU wants to be carbon neutral by 2050, and has various other legislations that it put out and rules in terms of how you should do reporting and all those kind of aspects. Some things are being rediscussed and debated at the moment. For example, the regulations against greenwashing has been put on pause. But we do see that just not on an EU level, but on a national level, there are laws getting put into place to also enforce that. And at the same time, the EU does still really believe in its goals. And like in 2040, it's planning to have a minus 90% reduction in emissions. And also recently, there is the Clean Industrial Deal, which has been announced and will be enforced soon, which all lead really towards a trend of the European sector in general wants to do more and more sustainability aspects and looking into more and more of those sustainability aspects. But then in the space sector itself, we are also seeing positive development in terms of today and what's happening tomorrow. So there is currently national laws, like in Italy, which include life cycle assessment as a requirement, but also national agencies, like the French agency wants to include LCA more and more. ESA is doing it actually also in their own internal projects. And in the future, we will have the ESA guidelines, which will be published soon. The product environmental footprint category rule for space, so that's standardized methodology on how to do LCA, and the EU Space Act, which are all coming up in quick succession and being developed at the moment. So it's really about providing guidelines on how to do LCA in space, and then providing a standard on how to do it and how to implement it into law as well, and then actually enforcing it through the EU Space Act as well. So we are really seeing a strength, and that's what EPFL actually saw a bit ahead of the curve. This curve will be happening, and that's why this project was being created. So what ESA needed, so they expected really these requirements and that the industry would need LCAs. And in the upcoming ministerial as well, they really identified various aspects that are being touched upon during this project, like simplified LCA, and maybe doing AI-driven aspects. So we also include that, first versions of it. And eventually, what React wants to do is also connect with other tools like model-based system engineering tools. And we actually see that the industry itself feels this pressure that I showed you before, and that there's a need for a tool like we're developing. Feel free to also comment if you have comments about this, if you feel the pressure or not. It's also interesting for us. And when you do comment, by the way, I think Mathieu didn't say it, you can always re-upload a new message if needed. You can click on a link. There is what we see, however, is that especially small and medium companies don't quite have the expertise at the moment. So the tool needs to be simple if we develop a tool. And there is an issue with the data in the space sector because it's all very private and you don't want to share it too much. So that's why it was key for us to make a tool that was not online and that everything about the data is here in person. Let's discuss a consortium, but I'll let Mathieu do this. You?
Yes, to finish this introduction, I'd like to have each entity of this consortium coming up just to introduce themselves quickly. You see that the organization, we started with the first proof of concept project in 2022, and we were EPFL, Ateleris, and the Scherrer Institute working together. And then we extended for this second phase, bringing new expertise also to complement for the project. And we set up also an advisory board with support from industry to just have an external point of view also. So first of all, thank you very much to all this consortium. I think it was for us a very successful project. We are happy to be part of this. And I will let everybody introduce themselves quickly. First, maybe Emmanuel for EPFL.
Yeah, so the first part, EPFL, so the EPFL Space Center, we're leading this activity, doing the management and the system engineering. Why EPFL Space Center? Because we also have a long expertise around space sustainability, system engineering, and also education for students on space technologies.
So I'm Karin Treyer from Scherrer Institute. This is a research institute in Switzerland, and I'm working in the lab for energy systems analysis, and specifically in the technology assessment group. And what we do there is life cycle assessment in the energy system, risks and costs of technologies and the energy system. And then we also put all these different indicators and criteria together in multi-criteria decision analysis, which wasn't part of this project. This project, we put in our expertise in the LCA methodology. We have in-house developed open Python-based tools. We are really developing new packages for prospective and dynamic LCA. And basically, I didn't come from the aerospace side, but really from this LCA expertise.
And you will hear more about it later. Now, Ateleris.
Thank you so much. I'm Laszlo from Ateleris. It's also a software company in Switzerland. I would also like to mention Aurel, who did most of that wonderful work in the platform development, also Sylvain, who is supporting him. What we do is software engineering, sort of a comprehensive service. Here, what we help is really help guide the team through this process of, we have a vision, we have an idea to see how could this come to fruition in terms of building a platform, then building a platform, and also maintaining and building it out, and really bring those ideas that there are into features and make them usable. We have a heritage in software engineering for the ground segment, but also, which is relevant here, but also for the flight segment. Really try to bring this end to end together to build something new. Thank you so much for this wonderful collaboration.
Thanks. Jan for University of Stuttgart.
Yeah, good afternoon. I'm Jan Fischer. My name. I'm research associate at the University of Stuttgart. So our institute has a strong background in space system engineering. And since 4 years, we are also researching on life cycle assessment of launches. And during this project, we implemented the launch emission calculation and re-entry emission calculation, which is quite new in the field.
Thank you. Alice?
Yeah. So my name is Alice, and I'm a postdoctoral researcher at ISAE SUPAERO in Toulouse. So it's a French engineering school. Basically, we are part of a big lab, more working on space mission design. And so there is everything related to that. So what I do, multidisciplinary design, analysis and optimization, but also orbital mechanics, propulsion, and LCA methodology for any kind of space mission. So can go to the lunar habitat until the launcher design. So what I do. So here for the REACT project, we are more involved into the launch trajectory. So we are going to talk about that later. But it's also important here to say that we are also really focusing on the eco-design approach of a launcher. So this is really related to the work here. So really happy to be there and to have done this collaboration.
Thank you. Erika.
So Erika Wolf from WaysEhead. WaysEhead is a consulting firm, French consulting firm based between Paris and Toulouse. We have a strong expertise in sustainability and ESG regulation with a focus on strong focus on the space sector. And our small insight in this huge project was to see to which extent REACT could address some expectation or objectives on ongoing regulation in Europe. And thank you for this opportunity to join this consortium.
Thank you, all of you. So you will hear from them later, in also explaining the results of this project bit by bit.
Yep, thank you, Matthew. So now that you've heard about the consortium a bit and that I've given you the background on why this project was relevant, let's actually discuss the project that we've done and timeline-wise. So you can see it here. It actually, the very first phase began all the way back into 2023. So it's a long-term project. And now the one that we're going to present here is it's phase 2 of the project, and we're coming to the end. You can see where we are today. Where we really focused on extending the software and developing it further. So the key focus was to align ACT with the industry needs. So that's what various partners helped us with, and integrate it into LCA and integrate also the developments that are going on, product environmental footprint development, and so on. And the goal afterwards is to put this tool, make it available for the industry itself, and implement it and continue the development essentially of the tool with also industry. So maybe the people online might be interested in the tool. We'll show you afterwards what the plans are for the future. A brief pitch for the tool. That's always a sentence we say, that ACT is a space-specific tool for simplified and prospective LCA. So the prospective aspect, for those not familiar, but it will be discussed, I think, is about if you design a future system which will be launched in 10, 20 years with your technology for various components might evolve and become more environmentally friendly, let's say. That's what prospective does. It takes into account the future aspects of LCA. So the tool is really about a simplified tool, prospective tool that can do also LCA more detailed as your design advances, and help with eco-designing and decision-making. So you can include not only performance, cost, and availability when choosing, for example, a propulsion system, but also sustainability aspects. Or you can do more high-level mission architecture comparisons. Should you launch your satellites with one big launcher, or rather with many small ones, or should they be reusable to some extent? This is what you can do in the comparison part of the tool as well. It's quite useful for the industry. I'll let Karine discuss exactly the LCA methodology.
Thank you, Monix. So I will talk for the next 20 minutes. Monix will stop me if I'll take too long. And what I will show you is lifecycle assessment, the methodology, how we developed it further together with many people active in the space sector, and how we implemented it in the tool which Monix has just presented. I don't know if everybody in the audience is familiar with lifecycle assessment. It's used for quantifying environmental impacts of products or services over their whole life cycle. And it's currently the best method to do that. It's standardized into ISO standards. And these ISO standards are basically the basis. Then there are other regulations or standards which are built on top of these ISO standards, and that's also what we follow. So basically, the ISO standards say that each LCA is structured in 4 phases. And that's goal and scope definition. So why do I do a certain study? What do I want to find out? What are the use cases of such an LCA software? And which questions can be answered? And then the next phase is collecting data. And that's usually the most time-consuming phase, the most tough phase also, because often data are not readily available. And such a software needs to do all this data management. So they need to help the user to bring all these data together and then turn it into into a format so that we can use it in impact assessment. And then the life cycle impact assessment is the turning these data into actual environmental impacts. And then, so this is the 3rd phase, and then we also have interpretation phase, which basically runs in an iterative way over the whole study. So we need to visualize results in ACT so that we can actually conclude what are environmental hotspots, where do they happen, and how can we actually support eco-design with LCA. Besides the data, so the data are the backbone of every LCA study, so it's hard to get them, but then also the LCA methodology is one backbone. And I would say we have to look at this methodology in 2 different ways. So there is the scientific methodological part. We have identified some gaps, which I show you later, which so that LCA as such is not yet fit for space-specific purposes. It needs to be made space-specific. I will talk about that. But then there are standards and guidelines and regulations which exist, which have to be followed. And of course, we have aligned with the ISAE Space LCA handbook and also the ISO norms. And people of the consortium have also been or are involved in the PEFCR for space group. Then, of course, if we want to do an LCA, it's not enough to just have a nice methodology, but it also needs to be user-friendly. So users, I mean, if you maybe as engineers want to put in data, you want to have nice input and export functions for feeding data into the LCA. You want to see the results calculation and then also visualization. There also exist different modes of ACT for different user groups. I think that will be mentioned later. So we have, when you want to find out something about eco-design of your product or system, we have the ISO phases. We need data. I will talk about that. We need tools. These are certain tools which we are using. This can be used by ISAE, by industry, academics, and regulators. This, we can maybe try not to harm our world too much with the space sector. Just for you, in the slides, we have placed the ISO steps just for you to know that this is kind of normal LCA. We have also put this icon to show you this is how we implemented it in ACT. And then during the project, the 2nd phase of the project, we realized together with FLPP and ISAE Clean Space that there is a need of some simplified LCA. Because engineers at early design phases, they don't always have all the data which are needed to do a full LCA. They don't have the time maybe also and the expertise to do such a full LCA. So the consortium was asked to develop, together again with ISAE and other people, a simplified LCA definition. And this is the definition which is also which was also presented by the ISAE ecodesign task force. It's a streamlined LCA methodology focusing on a limited level of detail, including reduced scope, data collection, analysis, and the presentation of results, while providing still some valuable insights for decision making and without compromising the credibility of the outcomes. It's a bit of a difficult thing to actually really combine all these, but yeah, we think that ACT can actually help in succeeding there. Of course, it relies on reduced details and proxies. Of course, the results can be wrong, so you need to carefully interpret your data with robustness judgment. And space-specific aspects like emissions in upper atmospheric layers should not be neglected, even if it's a simplified LCA. So when we started, basically the idea was, let's do an LCA in the space sector. So this is how we would do that. We go to the ISO norms, we go to the ISAE LCA handbook, which was already a great basis, and then let's just define the goal and scope, which needs to have space-specific boundaries and also space-specific functional units. We need to have life cycle inventory data, which need to be documented, transparent, traceable, and as complete as possible. And then we would calculate the environmental impact based on those data. The recommendation of the ISAE handbook is to use the environmental footprint method for that, which we also implemented. And then we let users interpret their results. But the problem was that there are some specific aspects which are specific to the space sector. So we can't just take LCA as it is and apply it one-to-one to the space sector. In the space sector, we have long design cycles. We have a very international industry. There is extensive testing. We have usage of specific materials, which are maybe just produced in low production volumes. Then there is transportation with maybe special vessels to the launch site. And then during the launch phase, we have these emissions into high atmosphere, which might have an effect on the ozone layer and on climate change. And this is where we have a data gap, or basically a scientific knowledge gap. And more research is needed to understand which emissions do we have in which atmospheric layers and how do they translate into environmental impacts. And only once we will have those data, we will be able to implement that in the LCA of space systems. We have long mission use phases, which also gives us, again, a bit together with the long design cycles, this prospective aspect. And then during the end of life phase, we have, again, emissions in high atmosphere. And then again, we need to know more about the impacts. So let's go back. So when we want to do space-specific LCA, for the goal and scope, we need to extend our geographical scope and the system boundaries, just not only like normal LCA from the Earth ground, but also really going up to the upper atmospheric layers and even to the orbits. And try to make some conclusions, try to find out some conclusions on what happens up there in these environments. For the inventory data, we have already the ISAE LCA database, which is space-specific. We did not implement the StratGlide space database yet in ACT, and we implemented this prospective aspect. I will show you how. And we use, of course, the recommended environmental footprint lifecycle impact assessment method, but we have also tried to bring in some more of these space-specific impact categories to the extent which is possible today. And because such space LCA methods don't exist yet, we show some results on different levels. So we don't always show real environmental impacts, but sometimes we just do what we can, which is a mass flow representation. So we can already show mass flows into the atmosphere from a specific launch in a specific trajectory, which comes from ALICES. So that's really ALICES and Jan Steffen's work, trajectories. and propellants, engine, and so on, and then which emissions do we have in the atmosphere. We also show the REACH chemicals used. We don't show yet mass flows to deep sea and use of critical raw materials. And we are in the consortium also involved in developing such novel metrics. So this is, you will see it later on when we will have the guided tour in the software. This is, for example, how we can show emissions per altitude, different species at the different altitude layers, and also how we coupled our life cycle inventory to the REACH tool from ISAE, which exists. So now what I'm going to do is I'm going through all these 4 phases of LCA, and I'll show you how exactly LCA can be done in ACT with answering specific questions. So first phase is goal and scope, where we say, why do we do something? So a goal in the space sector of doing an LCA, of course, to support ecodesign, is usually to quantify or screen for environmental impacts. We might want to compare different design options to, should you go for a bio-based material, should you go for reusable launchers? And we also want to evaluate trade-offs between these different design options, but also between different environmental categories. So it can be that we reduce climate change impact, but we increase maybe use of materials or toxic effects. So like this, we can inform decision makers or engineers, society, other stakeholders. In the goal, we also set the so-called functional unit, which gives us the comparison basis. This can be set for the space or ground or launch segment specifically, or for individual project materials. So should we use, again, the bio-based material, or it can also be set for the full, for a full mission. So we can say we want to look at the environmental impacts of a full mission. And the reference flow then gives the amount of products or services which are necessary to fulfill that functional unit. Now in the simplified LCA, which we have been asked to develop, that's usually similar questions. Typically, simplified LCA is done in early project phases where you have little knowledge on the data and you specific knowledge on your system. But still, it's similar questions. You might have still the same functional unit, but maybe for a bit of a smaller system. And the results absolutely must not be used for external claims because the uncertainties are just simply too high. Still, it's of value because it makes you think of the life cycle aspect of your system, and it can give you valuable insights into eco-design decisions. Still in the first phase, we also set the scope, which means the system boundaries, for example. These are key for the credibility of the study outcomes because you can do greenwashing if you set your system boundaries in a clever way, which we shouldn't do. In ACT, we suggest different, we provide to you the information on different ISAE internal approaches. So for example, FLPP has life cycle steps for a full mission. ISAE also gives so-called phases, and in the user manual and in the background documentation, we show all these system boundaries to you, and you can, as a user, choose them themselves. Then the temporal scope, as implemented in ACT, is that you can do LCA of current systems, but also future systems up to 2050. The geographical scope, again, we extend from the Earth ground to higher atmospheric layers and orbits. Then for the data collection, how is data collection done? Unfortunately, because engineers couldn't tell us, we all work with this specific software, where we could have created an interface. So basically, each company, each ISAE department will have their own way of how they will collect their data, their in-house data, and ACT also provides background databases. Allocation, that's something which is needed when, for example, one launcher gives a shared right to different satellite owners. And then we have to decide which part of the environmental impacts of this one launch is allocated to the different satellites which are brought up to orbit. That's something which you just shortly described. Then we have developed a more detailed methodology regarding the reusability of launcher or launcher components, and the end of life with the demise, that's not yet completely solved. And I need to hurry up a bit. So for simplified LCA, of course, the system boundaries can be set much smaller, but that needs to be documented well. So prospective LCA, as Marnix has explained, we often have to look into the future because the launch or a specific launcher might only be present in future. So that means that your foreground data, you have to adapt them. You have to estimate how will this launcher look like in 10 years. We have to adjust the background data because the world will change quickly. And in theory, we'd also have to change the way how impact assessment is made. Because, for example, the background concentrations in the atmosphere of CO2 could change, and this could have an effect on the impacts of climate change. It's not yet done. That's something which we try to do in the LCA community, but there is no readily available solution for that yet. So what we do in ACT is we use a Python package which we have developed at PSI, which takes the Ecoinvent background database and it puts it together with the scenarios from integrated assessment models. And this way we can show scenarios for how would the world look like for different increases of global mean temperature for these time steps. And we don't have time to go into detail for that, but just for you to know that there is also, we describe that in our user manual and in the documentation. And there is also a dashboard which shows how these different scenarios look like. So the only thing we do is we say using historical data for something which will happen in 10 years only is wrong. So we try to get results from such models which are out there, which are used in the IPCC report, for example, to couple them with our LCA. Then for the foreground, that's the case-specific data which you collect. It's something which has to be collected in-house. For simplified LCA, this can be limited just based on readily available data. You might also have data gaps, and ACT also provides you with some default values. In the background, ACT provides prospective databases, and it provides the ISAE LCA database and Ecoinvent. In a simplified LCA, you might want to use generic data sets, so for example, a market average or proxy data sets. What is important there is in lifecycle inventory, in this data collection, is that we have implemented the data quality rating. Of course, there are uncertainties, there are sensitivities, variabilities in an LCA. And you could also do quantitative uncertainty assessment with Monte Carlo. ACT could do that in theory, but that's quite complicated for user input. So what we have come up is a methodology which says the user has to give an estimate of how reliable is the amount which I put in. Do I know whether it's just a transport or it's transport with a specific vessel? And then also, did I find a data set which represents that well? And based on that, we will see later in the guided tour of ACT, we can kind of see if the results which we have produced are good enough to be interpreted or whether we have to do another iteration. Then for the impact assessment, the ISAE handbook, as mentioned, recommends the environmental footprint, and they also recommend the reduced interpretation set of 8 indicators. That's also described in the user manual. And ACT provides all of them. The LCA gaps, as mentioned, we have them, but we make this step forward by at least giving the mass flows and giving a space debris index for the orbits. In simplified LCA, you might just choose few categories. Please don't only choose climate change, because then you miss the trade-offs between different impact categories, for example. And then there's interpretation, finally, the last step, which is iterative. So you might, once you see the results, you might have to go back, maybe collect some more data, maybe adjust your goal and scope. In this phase, all the results from your data collection and environmental impact calculation are analyzed. Do they really help me to answer the questions I have set up in the goal and scope? Did I choose the appropriate system boundaries? And ACT helps you by visualizing the results of the impact assessment calculation. The validation of a user data input is not yet there. So like, for example, you have a launcher of a specific weight. ACT does not yet support you in double checking if your final lift-off weight is actually really correct or not. But this is something which will probably come. You're going to do completeness checks, consistency checks, and again, ACT supports there because it gives out a report which can be downloaded which supports with such interpretation. In simplified LCA, of course, you have to acknowledge all the uncertainties which are introduced to the simplified approach, and maybe you just do one or no big iterations. So you don't go back and improve the quality of your data much more anymore. And yeah, so with this, I'm at the end. So I think the major achievements which we have done over these past 3 years is that we have made LCA as space-specific as possible. So I think LCA done with ACT allows us to do LCA which goes beyond of kind of a normal plain LCA just done for the space sector. It's flexible enough, this software, to also follow all the future developments, because we expect that there will be more developments. We know that there will be more developments in terms of data availability. Maybe there will be more models like the ones Alice and Jan Steffen develop. We know that there will be further development of the life cycle impact assessment methods to account for these atmospheric impacts, for mass flows, maybe to deep sea. We also know that there will be methodological advancements in the LCA field, for example, for dynamic LCA, or to make prospective LCA better. And we also know that there will be more regulation and guidance coming up, and ACT should make it possible to actually also give the results for a specific regulation. So I would say ACT really does support users in eco-design decisions with the LCA it can do today. And I'm very sure that there are many questions around, but we will have the tour through the demonstration of the tool and also some time later on to discuss. That's it.
Thank you, Karin. So indeed, this LCA from simplified to full LCA, that can be done in different phases of the project for future space systems. And now, as you said, the tool is flexible to also be adapted in the future with new developments. So we will hear from Laszlo about the software architecture and how it was developed.
Thank you so much, Mathieu. Perfect. So I would like to do a quick deep dive into what we built. And I would like to start this with the software engineering process, because at the beginning we talked about vision scoping, finding out what we would like to do, and then actually build something that is around that vision. We heard a lot of input from Karin on what goes into that vision, how we want to work with this. So I think this is very important to start. And so this is representative of actually both phases, plus minus, where we just say we have a definition phase, implementation phase. At that point, we'll have feedback, and we go over potentially to having a CCN to actually add some more bells and whistles that were not envisioned at the very beginning. And so very importantly is when we started this project, we had visions, and for us, it was important to find out what would that be. So we were trying to build a sort of a frame, a box that would contain the vision goal, because we as a software provider may not know about that vision. So we have to find out what it is. So what we did at the beginning was sort of an iterative, agile loop where we tried to listen to what should be done, where we would like to go, try to bring this down in like processes and mock-ups, UI mock-ups. You'll see at the end what was actually implemented. So we do course mock-ups where it becomes more tangible. People can look at it, can give feedback. It's much more visual. And so we did this at the very beginning here in this definition phase, where we looped through talking, putting in it in a graphic, maybe take a risk, get the requirements out of that, and then also some design elements. And so this was actually at the beginning of the phase, where we also ended up then still having a software requirements document and also software design documentation to really say this is basically where we build up. And the idea being, with the requirements, we built this frame, and with the design documentation, we started to fill in different items. These we then used, put into our backlog just for implementation, with description of what they mean, and we could then start here the implementation phase, where we would plug these items, implement them, maybe reprioritize them because we found out something may not be as important or something just became more important, and that we then did iteratively and grew out, got as well feedback, which then would go back into our backlog so we can implement this. So I think this was fairly good. I was involved in a different project that was more hardware driven, where this was not as agile, but for this platform development, it showed up to be quite useful. I feel fairly confident that this would also be applicable for other domains. Now, what is it that we built? This is sort of a solution overview. The idea being, if you look, this is you're using this platform. I'm not going into the actual elements of the UI because we will see that in a demonstration. So you are here, you want to use this. Then we have here this big corner, or this core framework, which is handling all the requests coming from here. There is clear APIs that we implemented in here in ASP.NET and C#, which may not be a technology that was often used. Usually, or often, these platforms are in Java. I will get to that a little later. So we decided, however, to go with C#. The interface here is with React. It's to build really flavorful applications or web applications that at the end run on your desktop in your browser. So are independent of the operating system. So we have interoperability. So this is sort of core framework here. We go out here in the back, connect, for example, then Keycloak to it, which we use to do login, provide secure login, which could also be used then to extend into the ESA tool universe if need be. And then here at this point, we heard about just before from Karin, we sort of change, we go from C# or this ASP.NET into the Python world, because a lot of the tools, also scientific analysis tools, are available in Python. So what we did is, instead of trying to get them into C#, we actually run them separately within Python and connected with sort of a software bridge that would allow us to grow this universe of tools without having to re-implement them in our own language, because then we have to maintain it, and there is a whole thing of things that we do not want to do. At the end, we're running all this within Docker containers in a Kubernetes cluster here in Azure, Switzerland for now. The idea here is really that all these elements are in a container. They're independent. They can be also set up at another place fairly easily with this, and also orchestrated there. So it's very flexible to move from one platform to another, because all these bits and pieces are really contained and can very easily be moved from one place to another, and also then operated in another environment if need be. Lastly, something that came in at the very end is this piece here. We integrated a new feature that allows us, using large language models, MCP, Model Context Protocol, where you can take an LCA specification in a document, in a PDF, and then you give it to the system, and the system will start building your LCA configuration in your tool. So here it's usually you sit down and you start, we'll see that later in the demonstration, you start doing your configuration, and then at the end you can have a report. And here basically you take the configuration as a document with text, you provide it, and the system will then build your configuration for you. Now, in terms of technologies, just a little quick recap. It's very technical, I know. It's the front end is the primary driver is React, again, to build full playful applications. Also with there was a lot of need to have also visualizations, interactive visualizations. Perfect, thank you, Matt. And then the backend, as I said, was done with C#, but also with a connection to Python to keep basically get these algorithms at our disposal. Security was done with Keycloak. I'll say a little bit more on one of the next slides. And then DevOps in terms of operations, as I said, was in Docker and Kubernetes. We also built these integration pipelines. There's no slide on this, but basically we have an environment that is for staging, so new stuff that comes out, for development where people can give feedback on a more or less stable platform. And then there is the operational platform where only after releases where we're sure it works, we will push it there. And so this is very easily, it can be easily done with this. Now the major design choices, it's a little bit of a repetition, but as Jérôme said at the autumn event, the repetition is good, so it sticks. There's two main frameworks that we used. So this is the main application in C# and .NET with the React frontend. As you see here, we chose this because it's very, very flexible. It is very, it's very interactive. It's also decoupled, which means we have here clear API connectors that we can then go to. That makes it more easily distributable. It's also more easily to extend if you have new functionality. And then because of a lot of the calculation algorithms were in Python, we have this Python block that is not integrated directly in our application, but sort of parallel, which again adds more flexibility also to scale. These algorithms may take time. And if you don't bring it all into the same application, we can also distribute the load a little better. In terms of performance and interoperability, this I already said, because of the time these calculations may take, we introduced also sometimes caching. So certain responses will come fairly quickly because we don't recalculate everything, but we have it pre-calculated. So at regular moments in time, we will recalculate to update the cache. But when you have a request, it will be fairly quick. And this I already said. And also the modular architecture, there is a few things that we have not yet implemented. There may be new things that are coming out that we would like to connect. And so we thought it was very good to have these blocks so we keep the flexibility in growing and adapting over time. Security, there was a very long discussion at the very beginning. Where should the data stay? How do we achieve separation between different clients? At the end, data is only stored in your local browser, 1 minute, and then it can be deleted. There's not going to be bleeding of data into different spaces. So this is separation. We have very fine-grained user access policies for ESA, for users, for developers, for admins that are predefined to accelerate also adding new people on board. Then this Keycloak for login purposes is sort of a standard that we use for login, which would allow us also to leverage that standard to integrate maybe other other platforms and allow the single sign-on. So you log in once and you can use that on different platforms. And we did some code testing and penetration tests towards the end, just check that we don't or that we didn't oversee any important flaws maybe in the software. And this I already said, so I think we go on to the software and more into the features and actually using the platform. Do you want me to continue here or you want to?
Thank you very much.
Perfect. Thank you so much.
Okay, now briefly, I will fly over some of the main features of the software, and we will hear a bit more detail about the special features about space-specific LCA. So just here you have the navigation bar screenshot from the tool, and to show you that it links back to what Karin presented before, that you find the different steps of the LCA, the goal and scope at the beginning to set up your goal of the study. Then you are guided through the lifecycle inventory step, and of course then the tool and the way it's computed, as shown by Laszlo, provides the results, and then you can navigate through those results, visualize them, and do the interpretation. So space-specific, it's also about space-specific building blocks. We started by allowing the design or the modeling of launch vehicles. This was the case for the proof of concept tool, and now in the second phase, we also extended with the space segment, the ground segment, and recently the user segment and some background infrastructures that you can add to your model, to your system boundaries. The inventory, so you would select a data set from those available databases and then provide additional informations like data quality rating that Karin explained, or ways to group the impacts once they are computed in the different plots that are provided. The configuration, so really the system level of what you want to model. We have the model templates for different types of systems, reusable and expandable launch vehicles, but also different segments, as I said. And you can start from scratch, so building from zero and defining all the inventory, or you can use one of those templates that is provided with the tool to kind of learn and also modify from them to maybe go quicker and get your simplified LCA results quicker. Here, quickly, some of the ways you can see the results, but we'll see it also in the second part. So bar charts with different LCA indicators grouped by different grouping types, so categories. Here, typically, lifecycle steps that were defined with FLPP, or the famous ESA project phases from A to F. Also, Sankey diagrams, which are widely used in the LCA community to understand where the environmental hotspots are. Single score formula to aggregate all the impacts into one value. So we use the PEF equations with normalizing and weighting the different indicators to put them on one plot together, and you can identify which ones are more relevant. And the data quality, so at the end you can get an overview image of what's the quality of your model, looking at different criteria, and it also helps you target and specifically focus on where you should collect better data for your next LCA iteration. Also, ways to compare different models. Once you have several systems that have the same function, the same functional unit, you can put them next to one another and compare in terms of environmental impacts. What's the difference? So typically changes in percentage of impacts for different categories here, or looking at the same single score as before, but next to each other to see if the hotspots are the same and if the final value is different. By the way, here also the single score, the absolute value does not really make sense alone, so it's nice to compare between different systems. And to highlight burden shift, you have this plot on the bottom of the slide to maybe see that some indicators get improved by modifying or making eco-design decisions, but maybe also it shifts the impact to another indicator, so you can see this with this type of plots. And now I will leave the floor first to Alice, talking about the trajectories and the space-specific impacts in higher altitude.
Thank you. So yes, so for the trajectories, you have as a user two options. The first one, which is the easiest one, if you're working in a company, for example, is to import your own trajectory directly following the input model of the launch emission calculation tool that Jan Stefan will present just afterward. And the other solution is we provided a library of already optimized trajectory for an expandable launcher. So it's Falcon 9 LOX RP1 kind of launcher, but launched from Kourou. And we provide this library of trajectory
so to different kind of missions, so LEO East, SSO, or even polar. I forgot to, I put it also, polar trajectories. And we will provide also, so it's not done yet, but we will provide also a GTO trajectories, so the one of Ariane 5. And then you have a different range of payload that you can use. So why we do that and why we don't directly optimize the trajectory inside the tool is because at the end, doing the mission analysis and the full trajectory optimization of the launcher, it's really a challenging task, and we need all the input that the user is going to give within ACT. So at the beginning, for example, the mission type, the payload mass, the mixture ratio, the pressure chamber of the diameter of the launcher. So all these kind of parameters that normally then we are using them in order to optimize the trajectory of the launcher for the missions we want. So it's not really something that it's implementable in the tool because it needs a high computational cost. And of course, there is we are using optimization algorithm for that, and so there is the need of hard skills in order to fine tune the algorithm and to see what to do if the problem does not converge. So that's why for the moment we decided to go with this library of trajectory, also because the uncertainties that we have between for the launch between 0 and 100 kilometers are not that different if we look at different kind of trajectories. So it's a first good approximate. But I will just give now, so this is the trajectory when you select in the tool. They will just give you the overview of the trajectory that you selected. And now I just want to give a quick outlook at how we could integrate also the optimization of the trajectory inside an optimization tool. So inside a tool that could be ACT, for example, but also taking into account all the other disciplines that we can have. So as you can see here, at the end, it's a multidisciplinary optimization problem because you have to simplify several disciplines: propulsion, structure, aerodynamics, trajectory, and then you should add this life cycle assessment methodology disciplines in order to then decide on some performance and constraints, objectives to choose the final design that you want. So this is the work we are currently doing at ISAE SUPAERO with CNES and ONERA. And the idea is to have this kind of optimization tool in which we have defined this simplified LCA. So again, like ACT, but again, more simplified than ACT. So it's again simplifying what is simplified. But the idea should be then inside these disciplines, that is depending on all the inputs you have on the other disciplines. So for example, the propellant mass that you will have optimized before in the trajectory, or the pressure chamber that we will have chosen, the mixture ratio that you would have optimized in the propulsion type. Then you have this simplified LCA in which in one part you try to estimate the launch emissions you will have. So this will be explained more in details by Jan-Stefan just afterwards. And you have the life cycle inventories that Karin just talked before, with all the background data and the foreground database. And then thanks to that, you can do a preliminary impact assessment of your tool, and you can extract some impact indicators that you desire. So for example, the global warming potential could be also water depletion, land use, or the use of minerals and metals, for example. And then within this matrix, you could put some objective value or some constraints within your tool in order then to make a trade-off between the performance of the launcher you have and its environmental impact. So this is what we are trying to look at, and I think it's also a good outlook that ACT could do in the future with that. So thank you. And now I would let the floor to Jan-Stefan for the emission calculation.
Now, when we have our trajectory, we would like to know what are the emissions during our ascent into space and back from space. So let's start with the ones to space with the launch emission calculation tool. So this tool is based on a two-step approach. First, we are calculating the emissions at the nozzle exit level here. This is done with a Cantera implementation. As an input parameter, we need the propellant type, the temperature of the propellant, the mixture ratio, nozzle ratio, and the combustion pressure. And then Cantera calculates with an equilibrium calculation the emissions at the nozzle exit level at the first step. In the second step, then we are also calculating the afterburning, so the interaction of the emissions that are emitted at the engine with the atmosphere and the surrounding. And this is also dependent, of course, of your trajectory, because the higher you get, the lower is the density and the lower is the mass flow of the interacting atmosphere. So this is here implemented with mass flow coming from the outside. We have here the NLMSIS atmospheric model implemented that gives out the atmospheric species and density at the local time, altitude, latitude, longitude. And with that, we are then calculating the final emissions. Of course, it's important to say currently there are a lot of uncertainties in this field because we don't have measurements on higher atmospheric emissions, but the tool is already there and we can further develop it in the future if we get better data. Now here we can see an example of the implementation in the tool itself. So this is an example of a two-stage liquid oxygen, liquid hydrogen launcher with solid boosters. So here in the lower layers, we see here also the emissions from aluminum oxide, from chlorine, and in the upper layers, there's the emissions from hydrogen and water. This is the mass flow that you get within the tool. And this can then later, if we have the characterization factors in the future, also transfer to implants. Now let's talk about the way back from space to Earth. If we have here the mice in upper stage like this one, we've implemented the drama tool here to calculate the mass loss within the atmosphere, depending on the geometry, depending on the mass, the material of the launcher, and the entry conditions. And with that, we can then calculate in the second step also here the emissions. This is also done in a two-step process. One is the calculation of nitrous oxide using Cantera equilibrium calculation. So we assume here we have the shock wave of the supersonic space debris coming in, which heats up the atmosphere, and this leads to the formation of NOx. And then the second step is the calculation of the material. For this, we currently have the implementation of database. The tool also provides a CEA license, CEA implementation, but this would require an additional license. So here we approach with a database approach. So, and with this, again, here we calculate, the database is based on a calculation which was done at the university. Also here, the different atmospheric layers were taken into account. And in the end, we would like to know, of course, the impacts of all those emissions. Currently, what we have in literature is shown here. We have surface emissions, which are reported in the IPCC report, and we have some factors from aviation emissions, which are reported in the LEAD publication. But it's very important that for the higher atmospheric emissions, we do not have at the moment characterization factors, and they are now step by step going more and more research projects, and we will stick to those research projects also in the future to implement the knowledge that is developed in the future from this. And this also ends my part here, and I'm giving back the presentation to my dear.
Thank you, Jan. So we are almost at the break, so half time. Just a few more slides about other features. So Karin mentioned before the reach compatibility. So indeed, once you have made your inventory of materials that are part of your model, almost for free, you can get some information about reach risks. So those reach, for those who don't know, are regulations about materials and substances that are banned to use because of their toxicity. So we can now link our tool, ACT, with the ESA REACH tool that is mapping those chemical substances. And this gives an additional information about potential obsolescence risks for materials and substances used in your system. Another thing is we have documentation directly integrated in the tool so that we can guide non-experts and also regular users for step-by-step how to create their configurations and how to run the different models, and also some information about simplified LCA, etc., everything that we have been presenting today. And finally, we might see it also in the demo later. For implementing the prospective scenarios, you simply select your model, one of the 3 scenarios that is available in the tool, your time step at which you want to analyze it, and you can also compare different configurations at this time step. The 3 scenarios are written here, but basically you have some that are more or less optimistic regarding the future, and you can really look at the range of potential impacts that your system might generate in the future. Here we are, so we have a 10-minute break. Thank you very much, and see you around.
Okay, so for people online, we are slowly getting back on stage. The idea was also to take a few of your questions. Thank you very much for all the questions that you sent, and we just go through some of them now and try to address most of them.
Okay, clarification on emission, Corinne?
Mm-hmm. I would say it's any artificial. So the question is, how is the term emissions technically defined within this project? And I would say it's an artificial input into the atmosphere of a particle, which will then undergo a certain fate.
Mm-hmm. And Jan, about the area of the, so the emissions of the launchers are collected relative to an area?
Yeah, exactly. So this area is dependent on the launcher diameter or the launcher square area, and then it's multiplied by an effective.
Yes, thank you.
Then there was a question whether the considered so what are the considered propellants for the worst case future scenario which we implement? So we have shown that we implement 3 different future scenarios, and the question is which propellant is considered for the worst case. The propellant choice is something which is in the foreground. So that's something which you as a user, as an engineer, have to define. You have to say, today we are still using kerosene. In 2030, we are going to use liquid hydrogen, oxygen, for example. So that's a choice you do. In the background scenarios, that's not part of these scenarios.
Mm-hmm. I hope this answers the questions. If not, then you can ask for clarification or reach out to us as well. So whether ACT will be used by the industry, yes, and we'll talk about this at the end. General question on if we discussed with CNES, yes, because OASIS is a different tool, much more early stage LCA for those who are not familiar with it. We are talking with them as well to see if there is synergies possible between our 2 tools. We do think there is synergies rather than a risk of collision, but we are discussing this. Do you want to address the simplified LCA question? So can you confirm that in the case of a simplified LCA, the tool proposes hypotheses to take in case the data are not available?
So basically, if you have a data gap or you don't know yet how this will look like, the question is whether ACT will propose a certain value or material for that. Currently, we just have some very easy templates which could help you there. I doubt it. In future, we will take whatever the PEFCR will provide. So the PEFCR will come up with generic datasets and with template datasets, and ACT will take that. So far, I would say ACT gives you some hints on a very limited extent.
Mm-hmm. Yeah. Ecoinvent is indeed used. And we also use, for example, the ESA database, but users can also input their database. I think Mathieu will show it, or will show the button at least.
Yeah, they can create their own data sets in the tool, and the idea of extending with more databases is also, Karina, you mentioned the Strathclyde space database. This is not yet there, but it could be in the future, yes.
For data quality, Mathieu, you'll show it when you show the tool, but
yeah,
the quick answer is no, we don't necessarily use
there is also the ESA one, which is one more data quality input next to your data sets that you add in your inventory. In fact, we still went ahead with our data quality rating with 3 criteria, as we think it can help users know if they have to focus on getting better data about their own model, or if they need to create a better background data sets, or if they, for now, don't know enough about their system. So it helps them prioritize where to focus.
And some questions about the launcher. I think this was chosen because this is the data we had at the moment, and that's why we showed this for the Falcon 9. But for the trajectory, the optimization of the trajectory, someone want to add?
No, yeah, so what Alice is doing, she left, unfortunately, but you can decide on what is your optimization function. It can be the gross lift-off mass, or hopefully later on, maybe also a parameter that comes out of the LCA calculation in her slides. She showed maybe an equivalent to this global warming potential that would work with high altitude emissions. That's an idea as well.
Yeah, license agreement will.
I think you repeat it for the people.
Sorry?
Yeah, so there's a question about if how the ESA database is shared with the tool. Basically, right now, the ESA database is in the tool with us, but for the beginning, we will not disseminate the tool itself. We will be using ourselves the tool as a service for customers, and there exists an Ecoinvent license, and therefore also the ESA access to the ESA database. Later on, for when the tool will be distributed with a license, we will need to have this sorted out for being able to distribute the Ecoinvent datasets. And yeah, I think
we can slowly move towards other things. External tools, we're looking into them.
Yeah, other ideas of external tools could be model-based system engineering tools, or for instance, the TEMIS tool that is being developed by Politecnico di Milano for the space debris risk assessment. So we will also monitor if there are new tools coming up on the market that would make an added value to be connected to the ACT.
There was another question whether scenarios can be chosen by the user for a specific time, for a specific country, and also which level of optimism you have for the future. The user cannot choose own ones. We have pre-chosen now the 3 scenarios which we have explained. That was a decision also together with ISAE Clean Space and ISAE FLPP. In theory, there will be many more scenarios which could be chosen, but ACT currently provides the 3 scenarios as discussed. So the user cannot input their own scenarios.
Okay, and then we have one maybe last question if you want to address it. How does the LCA work for prospective? And then I'll ask maybe if someone in the audience here has also a question. And after that, we can move to actually looking into the tool.
So the question is, in the prospective databases, how we deal with the case when a product does not exist yet. So if, for example, the future scenario provided by the integrated assessment model tells us that there will be hydrogen from electrolyzers and the data set is not yet there, then either we cannot include that, or what we have done at PSI is we try to fill those gaps. So we, based on our projects, based on projects by partners or from other people in the LCA community, we have filled those gaps with inventories which are publicly available on a GitHub repository. So either we do that manually, we fill that gap, or the product is not considered.
There's a question here in the room.
Yeah,
That
I put some on the tool, but I have one directly. You mentioned you had advisory board from the companies who accompanied you in the test of the tool. Did you do the test cases for them? I mean, for the companies that you mentioned in your consortium setup?
we have used the tool, but it was already one and a half year ago. So the tool has changed a lot in between with Ariane Group. The work was presented at the Ecodesign Days last year. And we have made also some tests through some student projects with industries where we had one student doing their master thesis, for instance, on site. This was the case at Latitude, for instance. But no, we are looking into making more tests. So right now we are doing our tests with publicly available data. But at some point we'd like to validate that indeed modeling with ACT provides similar results than with other LCA softwares that are not space specific.
Okay.
And we are bringing the more space specific models on top of them. Yes.
Okay, so some people asked about the MBSE, so that's something we mentioned during the presentation. And the question is, how will it interact? So that's something we're looking into at the moment. And an interesting feature about the API, that's kind of similar trend. So we want to make sure the tool is compatible with other tools.
Yeah. Just to mention also quickly, we've made some tests with the Comet tool, which is an MBSE tool used in the concurrent design facilities. So through the Excel sheet, you can also already connect somehow to another tool. But then we are looking at if we want to connect with more robust APIs to some tools that offer this option.
So for integrating impacts of ground segments and such, I hope you briefly maybe showed it, but there are building blocks for ground segment and user segment and those kind of aspects. So you can actually build your ground segment.
Yes, and then looking at the second part of the question, it's also you would find some data sets that model a clean room that has some unit of typically hours of use. And if you add these data sets to your building block, then you are modeling your clean room usage. I see one more question about that I don't think we addressed yet. So it's a question about who is the intended users of the tool. And it's maybe a good question also to finish this presentation, because as Marnix presented the needs coming from ESA, but also from industries, the users of the tool or of the results of the tool will be space companies, especially in Europe, that have to comply to new requirements and regulations, or that want to themselves dig into the environmental impacts of their future and current space systems. The users themselves at first will be us providing the service, but it could be in the companies, could be systems engineers, life cycle assessment practitioners, eco-design teams, whoever is responsible and owning the tasks of looking at those impacts and trying to mitigate them. So it can be some engineers, and in also the project looking at simplified LCA, it was thought about what can be simplified also in the process, so that someone that is not an LCA expert can also use the tool, being guided by the documentation and by the flow of information to be able to use the tool. So maybe also project managers, if they are introduced to the tool, or they could start also using the tool and get a first approximation of the impacts of their systems. Okay, so for wrapping up this presentation, you've seen that it's a total of a 3-year-long project. We are at the end of the second phase with ESA FLPP, mixing expertise to meet the requirements with this great consortium that brings each of the entity brings a part of the solution. We are developing this tool to anticipate needs about life cycle assessment, environmental impacts. That will come from new regulations and requirements. This has been confirmed also recently with what we see happening in the space sector. And it's a browser app built on open source framework with some added functionalities and compatibilities with external tools. So to remind the catchphrase, ACT is a space-specific tool for simplified and prospective LCA. In a broader view of the perspective, so there are things happening in parallel to this project, some activities about research, for instance, and methodology harmonization also happening across Europe. And I will mention a few here. The SLICE project looking at high altitude emissions and impacts from launch vehicles that will start in 2026 with 18 PhDs. There are measurements being done. There are the methodology with the PEFCR for space that are being defined or refined, and some others. Just to say that this tool has been thought also to be ready to adapt and include updates for staying at the state of the art once any results come out of these different activities. We also want to prepare for a larger dissemination. So at first, we will keep using the tool as a service for companies, but in the years to come, the idea is also to have the tool made available for direct use by the industry. And in any case, if we see that there are new needs or that the context is also changing, we are ready to adapt to it and provide the solution that is really needed. So I come back to this timeline. As Marnix mentioned before, we are now very much at the end of the second phase and starting to get into operations very soon. So we are now looking ahead at what comes after this ESA project once we have delivered. And for that, I'm giving the floor to Jan.
Okay, so Mathieu, Marnix, Emmanuel, and I have created a startup, EcoDeltaV. This will be a spin-out of our EPFL and University of Stuttgart. And as Mathieu already mentioned at the beginning, we will start with a tool-based consultancy service doing LCA studies for space industry, and then refine the ACT tool further so that it matches the industry needs to be then also offered to the industry itself. So if you're interested, getting in touch with us, here's the QR code, and we also have a website where you can contact us. Here's the team. Mathieu, our system engineer, Marnix, our ecodesign consultant, Emmanuel, our advisor, and myself with my scientific background in LCA launches. And now back to Mathieu, who will.
With that, yeah, I hope that we covered all your questions. Again, I would like to thank first ISA for hosting us here today. It's a very nice room. Also the consortium that participated in this project. Altogether, I think we achieved a very nice outcome. And also, yeah, thanking you for attending and asking all your questions that are also helping us understanding what's the outcome of this project. Also, thank you for those online that joined us to listen to this presentation. Maybe one last word from Valère?
Yes, of course. The things I did not mention, or you probably noticed, is quite unique too. But a lot of publications also have been, how many publications?
4 or 5.
4 or 5, one also in the coming.
Yeah.
So that's just a message to say it's really is a state-of-the-art development. So still in development, still evolving. And I really also like Laszlo design for the software overview, because I think the team was also working like this. And that's also a special thanks to your attitude in that, because it was quite learn by doing, because it's super unique. And this is not the standard in ESA in general, but that worked. So it's my turn to thank you for that. So